drive the same acceleration. But if it's the same acceleration, but it has more mass, what does that mean about the net force? It has to be larger, right? We need a larger net force on mass 2, right? Remember, both of these masses are going to accelerate together because they're attached, but they are not the same mass. The bigger mass is going to need a larger difference in the forces that are acting on it. So this is a bigger gap. Because the gap here, the bigger difference, because what is that difference? It's the net force, right? So the tension is actually, if you wrote these down on a number line, it would look like this. The tension is actually closer to the smaller mass or smaller weight and further from the bigger weight because the difference of these two is the net force on 1, and the difference of these two is the net force on 2. And we know that has to be larger because it's a larger mass being given the same acceleration. Okay? Okay? Does that make sense? So that's why the tension doesn't wind up halfway in between. Because if it wound up halfway in between, what that would mean is that the difference with the tension in either weight was the same, which would mean the two masses experience the same net force. And that's not possible because they have the same acceleration, but they're different masses. Okay? So that's a pretty in-depth discussion on this system. And you can take this more or less to any pulley system, and there's not that many more things that can happen. In fact, let me show you about as complicated of a pulley problem as you can have. I'm not going to do the whole thing, but I'll kind of sketch it out. I think there's stuff like this on the homework as well. You could have a pulley problem like this. I guess that's not the very most complicated, but I wanted to show you what would you do for something like that. Well, one of the things that you might think is we've been using x and y axes like this on an incline, right? We pick one axis to be parallel, one to be perpendicular. And that's certainly not very helpful for this one, so don't use the same axes. We got lucky in the last example that the same y-axis could account for both of these objects, but here, go ahead and pretend that these are completely different objects, okay? So basically, this is like two single object problems in one. You can go right down to thinking of them as having their own set of axes. Then, what you go ahead and do is that they aren't, of course, totally independent one body problems. It's not like they're different problems on the homework. You're setting up one mass, the other mass, and then the connective tissue is that the tensions are going to be equal. So the amount of tension on both is going to be the same. That's how you tie them together. And then, of course, you write down some equation where you recognize that the objects have coordinated motion. So in this particular case, you know this one's going to accelerate like this, let's say, and this one's going to accelerate like this. So it looks like what I would say is that if, say, this acceleration, ax for 1, was plus 5 meters per second squared, that's in the positive x direction, this one would then have to be what? Negative 5, right? It's got to have the same size of acceleration because they're attached. And I happen to have set the y direction to be opposite the motion here. So in this case, my coordinated motion statement would be ax1 equals minus ay2. Okay? And again, the minus sign is simply because your axis choice was plus for one object and minus for the other. If you don't like that, some people just prefer to set the plus y to be downward, in which case you can say that's plus. That's totally fine. Then you don't need the minus sign here. You can just say they're equal. But of course, you'd have to be careful on the other side, because now your tension being upward would be negative and your gravity downward would be positive. So you have to be true to your signs, of course, once you've picked your axis. Are there any questions on that? Okay, so that's how you can think of pulley problems, right? It's basically two objects, two one-dimensional, two independent objects, and you'd have some connective tissue to tie them together because they're attached by a rope. Okay, so moving forward, we get to the next and final force that'll be included on your first exam, and that's friction. Force of friction. I will use F sub F for friction. Very commonly, you will also see it as this weird script-looking F. So that's supposed to indicate not just any force, but because it's a script, somehow it's friction. So I think that's what the book uses. Now, friction force, I should give some background. It's a very complicated force. And we would not ever try to introduce it in a course of this level, except for it's so prevalent in everyday life that we have to acknowledge the presence of friction in some way. And what we're going to do is it's going to be a very simplistic approach. It's not perfect. It doesn't work all the time. It doesn't work perfectly. It's empirical, which means that it's derived from experiment. And it kind of just gets the job done in situations that we typically see. Okay. So I guess let me first write down. The force of friction is complicated enough. We want to split it off into a two-pronged attack. Force of static friction. So we need to discuss the size and direction. And the force of kinetic friction. And we need to talk about the size and direction of that. These are two different types of friction. Or I should say these are two different instances where friction is relevant. You would never use them simultaneously. Use one or the other. So, what are they? Kinetic friction is probably what you're more used to thinking about friction. This is kinetic friction. So you have two surfaces that slide over one another. They're sliding across each other. And so the force of kinetic friction is for when the object is sliding with respect to the surface it's on. If you don't use that abbreviation, WRT, with respect to, you might want to jot it down. The force of static friction is the kind of friction that prevents you from moving something. So for instance, this table, I can exert a horizontal force on it, by leaning on it, it doesn't go anywhere. Obviously, there has to be a horizontal force counteracting that if it's going to stay at rest, and that is called static friction. So this is when an object is at rest with respect to the surface it's on. So you can see that those things are mutually exclusive. So you would only use one or the other, never both. Friction is a contrarian force. It always acts opposite. So for the kinetic friction, it's opposite the actual motion, the actual sliding. And for the force of static friction, of course, there is no motion across the surface, but it is opposing the motion that would happen. So this is acting opposite the potential motion. Okay, so obviously there's not a whole lot of difference in the direction part. It's the sizes that you really have to watch out for, and that's why we split this off into a two-pronged attack. Oh, and I forgot to mention my notation. So force of static friction, that'll be force of friction, comma, static. If I want to refer to just the size of it, of course I omit the vector hat. And then force of kinetic friction, force of friction, comma, kinetic. And again, if I want to refer to just the size, omit the vector hat. Now you can of course see there that it's starting to be a list of subscripts. You have to say it's friction and then what kind. And that's, I think, what the script F is for. The script F is so that you can only put one subscript. What kind of friction is it, static or kinetic? Okay. So what I want to do is I'm going to give you a little bit of a preview of the size, and then I'll go back and I'll explain what's going on. The force of static friction, the size varies. And for the kinetic friction, it doesn't. So that's going to be the major reason why we do not try to do friction all at once. We split it off into two approaches. So let me go back and explain what these things mean. I'm going to start with kinetic friction. It's the easier one. It's not a variable force. It's a constant force. So let's talk about kinetic friction. So, rubbing my hands is an example of kinetic friction. Two surfaces sliding against one another. One of the things that you can probably already know, but if you went into a lab you can confirm it, is that if you press the surfaces harder against each other, it increases the friction, right? So if you push the surfaces harder into contact, you'll get more friction parallel as well, right? Does that seem like a obvious statement? Okay. So it turns out that empirically or experimentally, you can find out that the frictional force is directly proportional to the contact force between the surfaces. Now that little simple demonstration with my hands, I have certainly not proven that they are directly proportional. Maybe the force is proportional to the square of the contact force or something. But I'm telling you that if you carefully measured it, you would find that if you pushed your hands together twice as hard, you'd get twice as much friction. They're directly proportional. Okay? So we need a way to quantify the contact forces between surfaces. Let's think about how to do that. Well, oftentimes, gravity might be responsible for driving the contact. Gravity, the force of gravity pulling on an object, pulls it into contact with the surface. Common misconception is that it's just that. But of course, if I push my hands together like this, gravity has nothing to do with it. Gravity has nothing to do with how hard two things get pushed together horizontally. And likewise over here, maybe there's not just gravity driving contact, maybe there's an additional pushing force. Then you have more force driving contact than just gravity alone. Well, we have a perfect quantity which can summarize for us all of the force that is creating contact, because it's a force whose job is to cancel this. So the normal force's job is, of course, to kill the other two, and therefore the normal force is a perfect measure of the contact force. Okay? The normal force is a perfect aggregator for how much force the two surfaces are getting pushed against each other, because its job is to cancel off this force so that you don't actually go through the surface. You just get pushed into contact with it. So it's experimentally found that when you double the contact force, you'll double the force of friction. If you triple the contact force, you'll triple the friction, and so on and so forth. Okay? So you just have to take my word for that, or go and do your own experiment. It's not terribly difficult to do that. So the next thing is to say, well, are these two forces equal? They can't be equal because, as you probably know, if I push my hands together a certain amount, how much force I'm going to get this way doesn't just depend on that. It depends on, well, maybe I have two surfaces of ice or concrete, or there's different roughnesses, right? So it's not just how hard the two surfaces are pushed against each other, it's what the surfaces are made out of. Okay? So for that, to complete the formula, we introduce another variable to account for the surfaces that are being dealt with. And that variable is mu sub k. This is called the coefficient of kinetic friction. It's a measure of the roughness of the surface interaction. You can look these up in a table, so you can find out what's the value for concrete on concrete, or concrete on ice, or ice on ice, or Teflon on Teflon. It's basically, of course, both surfaces matter, although sometimes just when I'm lazy, I'll refer to it as roughness of the surface, okay, as if the bottom of the object doesn't matter. But of course, it really matters what the object is made out of as well as what surface it's on. Okay, both roughnesses contribute to this value. Okay. And you can see that for a fixed amount of normal force, okay, so if the amount of contact force is fixed, if mu k is larger, then the force of friction will be larger. So basically, as that number gets larger, you will have a larger frictional force.
What does it say after roughness of surface and what?
Interaction, that's the word interaction. It's the roughness of the surface interaction. So for instance, let's say you looked up in a table and you found that a pair of surfaces, or if I'm being lazy, just the roughness of the surface, let's say that it's given as 0.5. By the way, I guess I should mention it's a unitless quantity. It's a unitless quantity because it's a ratio of one force to another. Right? This is already in newtons, as is this. So it's a way of basically saying what is the ratio of two forces to one another. So if mu k, say, is 0.5, you looked up the certain roughness, surface roughness is 0.5. That means that on this surface, the force of friction will always be 0.5 times the contact force. So you get half as much force of friction parallel to the surface as you do contact force that they're being pushed into each other. Okay? And again, please don't take that as 0.5 newtons. That's not what it is. It's 0.5 or half of whatever the contact force is. You can always increase the frictional force by increasing the contact. But the frictional force will be half of whatever the contact is. Maybe you have a rougher surface, though. Maybe the mu k is 2. That means that the frictional force will always be 2 times the contact force. So I like to think of mu k as kind of like a power multiplier. Okay? It's a matter of telling you how much does the force of friction differ from the contact force. Okay? So you just multiply the contact force by that number, it'll tell you the frictional force. Okay? A common misconception is that this number can only range from 0 to 1. Not true. Okay? I've seen as high as maybe 2.2 or something like that. But ultimately, this is experimentally measured. So if someone claims that there's an upper limit to this, all you have to do is go out and find incredibly rough surfaces and show in a lab. If you found two surfaces that when you rub them against each other, the frictional force is 3 times their contact force, then the mu k is 3. Okay? So that's basically it. That's all there is to friction. 2 ingredients that you need to know to calculate a frictional force: how rough is the surface or surfaces of interaction, and how hard are they pushed together. Okay. Does anyone else think that there's something missing from this equation? Anything that you think should be in there that seems to be missing? Anything else that you normally associate with how much friction you get? Size, right? Surface area. How big is the object, right? So if you have an object like this on a surface, doesn't this area matter? It's got to be more than just contact force and roughness. Well, to a very high degree of, again, this is just a rough rule, okay? I don't mean to say this is the be end all of friction, but be all end all of friction, but this is going to work very well for us. Area doesn't matter. Or I should put in there, a better way to put it is area is actually already included, but not how you think. Here's what's happening. So when we say that the contact force matters, what are we really saying? Well, this is what happens. If you were to zoom in here and see how these two things are interacting, friction is born out of the fact that both surfaces have unevenness. Might look like that. When two things are touching, it doesn't literally mean, you know that when you zoom in on a surface, it's uneven, right? So they're not really touching everywhere. They're really, most of their interaction is coming from a few places where they're really in close proximity, right? So if you imagine the amount of places where it's actually touching is not at all the entire surface area, okay? It's just a few select locations, right, where they're really touching. Now, if you increase the contact force between these two, particularly if one of the surfaces or both of the surfaces are very bendy, right? Things that like a rubber or something like that, where their form is able to be changed. So what would happen is you're bending them more like this in the closer proximity, and now they're talking in more places than they used to. So now, instead of these microscopic sites, now it's all of these, okay? So the increase in the normal force is really an increase in the microscopic surface area, not the macroscopic surface area, which is really hard to saturate. You would have to push them incredibly hard together before you would run out of more places for them to interact, okay? So this is a measure of the microscopic surface area of contact. And that's actually more relevant than the macroscopic surface area, the literal length and width of the entire object. Because you don't get to talk everywhere along that length and width of area anyway. You get to talk in as many microscopic sites as you are pushing the things into contact and forcing more conversation, okay? So the actual length and width of the bottom of the object doesn't matter. If you need further evidence, look at the bottom of your running shoe. It's not made to maximize the rubber contact with the ground. It's not a solid piece. There's treads, right? There's lots of cutouts, okay? Why are those there? Well, it's made so that, for one reason, when you step down on some water, the water can get out of there, okay? So the water is vented because that would have a huge effect on the coefficient of friction, because the coefficient of friction between rubber and water is much less than rubber and concrete. It's the same idea with treads on tires, right? Okay, so it's not all about length and width, okay? This is really it. It's how hard are the two surfaces pushed into contact with each other, and what is the parameter that rates the roughness of the contact that you do get, okay? Are there any questions on that? Okay, so that's all you need to know. And the other thing I do want to point out that you guys remember in your projectile motion problems that it kind of proceeded along the x and y directions could be treated separately, but they shared one thing, right? What was the one thing they shared? Time, right? Time could be shared. Well, this also produces an interesting sharing between the x and y axes. Because oftentimes, if we set an x and y axis like this, the normal force is a y force, but the force of friction is an x force, and it does cause a coupling between them. Okay? This is assuming, I guess, that it's sliding this way. So it does create something else that you might be sharing between the x and y axes, because you might need to figure out the normal force from the y direction, but that normal force will also affect how big is one of the forces in the x direction, right? And you can't deny the fact that if you exert a force this way, the harder you exert a force on one axis, the more it affects a force on the other axis, right? So be prepared when you're doing force problems, like the ones you're doing